Just as promised, I'm back in the next video. Additive interval property of integrals. What is this saying? This is saying simply that if we have a curve and there's a point C in between different x values, all it's saying is that if I want to get the area from A all the way to B, that's equivalent to me saying the area from A to the point C, give me this value, plus then you go ahead and perform the same operations, and then the area from C to the point B. This number gives me another number, and then I get a number which is the total area. That's what this is saying. And you might say like, oh, that's too simple. Well, yeah, but we're moving into a little bit more complex problems where now my area looks something maybe like this, and then we're going from point A to point B, and we want to know what is this area, and then we want to know what this area is. So we need to know what this point C is in between, so we can find the integral from A to C of f of x, blah 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 blah. It gets more complicated, but it's nice. And then the integral from C to B under f of x, blah blah blah. Actually, this is considered area between two functions, and this is a topic that comes later on. There needs to be more to the formula here, but that is the thing. So let's see, how does this apply to an actual problem, an algebraic problem? The example, we have the find the integral from -1 to 1 of absolute value of x dx. Ooh, well, what is this saying? This is saying, well, do I know what this function looks like? Yeah, it's nice pretty little v. There you go. And it's saying from -1 all the way to 1. I was referring actually to this little triangle and this little triangle, something similar to what I was talking about. Well, what is this? This is a triangle of area base times height. The base is 1, the height is 1. 1 times 1 over 2, which is 1/2. Well, hey, if this is a triangle of area 1/2, well, then what happens on the other side? On the other side, we also have the same area, the same value, even though it's on the other side. So we say that this is also 1/2. So what is this integral? It's 1/2 plus 1/2, which is 1. Algebraically, it would have been written like this. This is nice. Pay attention. This is how you're going to have to rewrite them. This would have been equal to the integral from -1 to 0 of absolute value of x dx plus the integral from 0 to 1 of absolute value of x dx. This is 1/2 plus 1/2, which is equal to 1, which makes sense. Bring this baby over here and you get a square. Or you could have brought this baby over here and you get a square too. It depends. Good, good, good. More properties, more properties. Properties of definite integrals. Let's see. What is this saying? It's saying if f and g are integrable on A to B in closed interval, remember, because we need to start somewhere and we need to end somewhere. Integrals, we do closed interval. Differentiation, we do open intervals. Okay, remember that. But anyway, in case a constant, then the function kf and f plus or minus g are integrable on the closed interval a to b. What is it saying? To be honest, the way that I look at this is describing more like the algebraic properties. We're moving in that direction where we're no longer looking at the area under the curve, of geometric figures, but more of complex figure shapes. And these are like curvy functions and other stuff. So we should be able to do those algebraically. So that's what this property is really nice. So what is it saying? It's saying if I have a function and I have a constant times my function, I can actually grab my constant and bring it out, and now I have my constant times the integral from a to b of f of x dx. And now this might be a simpler function to integrate algebraically. Remember, go backwards, undo the power rule and all the cool stuff. What is the other property? It's saying that the area, under the function of two functions, plus the sum or the difference is actually equal to the integral of the first plus or minus the integral of the second. This applies mostly when we have a polynomial. We're going to be able to break those polynomials. We're going to be able to break those polynomials out, into smaller integrable parts rather than the whole polynomial itself, which is really nice. So those were some of the properties. So yeah, that's where I leave it. It's a short video. I have one more video for you, and I believe that is it for this section. All right.